Exploring the vastness of the cosmos has always pushed the boundaries of human ingenuity, and few challenges intrigue astrophysicists and engineers as much as the prospect of intergalactic travel. In today's discussion, we delve into the demanding technical requirements and theoretical underpinnings necessary to reach another galaxy. This ambition goes far beyond routine space missions, demanding innovations in propulsion, energy management, and life support systems while grappling with challenges posed by immense distances and extreme cosmic conditions. Our analysis examines both established and emerging technologies through a lens of rigorous scientific inquiry, all while maintaining a relaxed and friendly tone to foster clarity among seasoned experts. We will scrutinize the scales involved, addressing distances spanning millions of light years, and dissect intricate galactic structures that compound navigation complexities. Furthermore, our exploration will address the technological hurdles of sustaining human and robotic missions over durations far exceeding any existing benchmarks. The discussion will begin by defining the context of deep space travel and the evolution of our understanding of space exploration over the decades, and it will highlight how theoretical physics might eventually bridge the gap between science fiction ideas and viable engineering solutions. With precise, fact-driven analysis, we intend to provide a comprehensive overview that not only acquaints the audience with current challenges, but also inspires further inquiry into the frontier of intergalactic travel. This overview sets the stage for a detailed journey through both technological innovations and the societal impacts of venturing into the unknown cosmos. Now we confidently commence. Deep space travel is defined not merely by the ability to cross solar system distances, but by the pursuit of venturing well beyond local star clusters into uncharted intergalactic regions. This pursuit inherently combines complex physics, advanced engineering, and high-precision mission planning. Historically, space exploration began with orbital missions and progressively evolved to lunar landings and robotic probes to the outer planets. In these early missions, engineers and scientists designed vehicles on the scale of millions of dollars, with technologies that, while impressive, were limited by chemical propulsion and conventional power sources. Today, the ambition of reaching another galaxy pushes the envelope even further, requiring a fundamental rethinking of propulsion methods, energy utilization, and radiation shielding. Designing a mission to traverse distances in the order of millions, if not billions of light years, introduces a plethora of technical challenges. Even if a spacecraft could travel at speeds approaching that of light, the journey would span enormous timescales and expose the craft to cosmic radiation, interstellar particles, and gravitational anomalies. Additionally, sustaining an operational environment for either human or robotic payloads over such durations demands unprecedented levels of reliability and self-sustainability. Engineers must account for the gradual degradation of onboard equipment, the accumulation of micrometeoroid damage, and the unforeseen consequences of long-term exposure to the harsh vacuum and temperature extremes of space. Moreover, current models indicate that energy generation and propulsion systems capable of sustained acceleration are in a developmental stage, with experimental designs attempting to overcome the barriers posed by fuel mass and energy efficiency. As a result, theoretical models and simulation studies have become central to understanding the trajectory and dynamics of ultra-long-distance space travel. This multidisciplinary challenge pushes the frontiers of modern engineering and theoretical physics, requiring a blend of practical solutions and imaginative innovations to feasibly open the door to intergalactic journeys. The culmination of decades of research in astrophysics and aerospace engineering now brings us closer to transforming these theoretical models into tangible projects. Our continuous improvements in material science and quantum mechanics further contribute to this ambitious vision, laying essential groundwork for future breakthroughs. Galaxies are vast assemblies of stars, interstellar gas, dust, and dark matter, bound together by gravity in intricate and dynamic structures. These celestial systems come in multiple forms, including spirals, ellipticals, and irregulars, each characterized by distinct distribution patterns, rotational velocities, and density gradients. When we consider intergalactic travel, the sheer scale of these structures becomes evident. Distances between galactic cores can span hundreds of thousands to millions of light-years, creating a daunting challenge for any propulsion technology. The Milky Way, for instance, extends over 100,000 light-years in diameter, while neighboring galaxies like Andromeda are separated by approximately 2.5 million light-years, emphasizing the enormity of intergalactic voids. The internal structure of a galaxy is equally complex. Central bulges, spiral arms with regions of intense star formation, diffuse halos, and even supermassive black holes at the center contribute to a multifaceted gravitational environment. Navigating through such a system involves understanding not only the spatial distribution of these components, but also the interaction of gravitational fields that can significantly alter a spacecraft's trajectory. Moreover, cosmic obstacles such as dense molecular clouds, supernova remnants, and high-energy cosmic rays pose risks and potential hazards by damaging sensitive instrumentation and undermining structural integrity. Intergalactic space itself is far from empty. The interstellar medium filled with ionized gases, dust, and magnetic fields creates additional navigational challenges. Engineers and astrophysicists must calculate the effect of these phenomena over extended distances to design trajectories that mitigate risk. In many cases, computational models simulate the gravitational interplay between galaxies and dark matter filaments, helping to predict potential areas of turbulence or density fluctuations. Such data underscores the necessity of real-time autonomous navigation systems capable of responding to unexpected cosmic events. Additionally, researchers are examining how relativistic effects might be accentuated across these massive distances, where time dilation and gravitational lensing could complicate both measurement and communication. The cumulative effect of these vast spatial structures and cosmic hazards forms a backdrop against which deep space travel must be planned with precision and robust contingency protocols. Advancements in computational astrophysics and high-resolution simulations now allow scientists to model these phenomena with unprecedented accuracy. This detailed understanding of galactic environments informs the design of navigation systems and helps refine risk assessment matrices essential for mission planning. It is an evolving field that continues to reshape our strategies for safe passage through these cosmic landscapes. Innovative ideas drive future progress. In order to overcome the immense intergalactic distances, advanced propulsion systems must evolve well beyond conventional chemical rockets. Present propulsion systems, such as liquid fuel engines and solid rockets, are fundamentally limited by their specific impulse and fuel efficiency, making them impractical for journeys spanning millions of light years. Engineers are looking toward alternative propulsion technologies, including ion drives, nuclear thermal propulsion, and antimatter engines. Ion drives offer high fuel efficiency by accelerating ions through electric fields, yet they provide only a fraction of the thrust required for sustained acceleration. Nuclear thermal systems, on the other hand, provide greater thrust by using nuclear reactions to heat propellant, but they introduce challenges in reactor shielding and reliability over extended timeframes. Antimatter engines promise orders of magnitude improvement in energy density, yet the production, storage, and controlled annihilation of antimatter remain highly problematic. In parallel, theoretical concepts such as warp drives and faster-than-light (FTL) travel have gained traction in the scientific community. The principle behind a warp drive involves distorting spacetime itself, compressing space ahead of a spacecraft while expanding it behind, effectively creating a bubble within which the craft remains contained. Although this idea is supported by certain solutions to Einstein's field equations, significant energy requirements and the need for exotic matter with negative energy density currently place it in the realm of speculative physics. Other concepts, like traversable wormholes, offer potential shortcuts between distant points in spacetime. However, stabilizing a wormhole requires conditions that defy conventional matter-energy configurations. Energy generation and storage represent another critical pillar of deep space travel. Advanced reactor designs, including fusion reactors and next-generation fission systems, must be integrated with efficient energy storage solutions such as high-capacity batteries or superconducting magnetic energy storage. These systems must operate reliably over decades, if not centuries, because intergalactic travel demands sustained power output far exceeding current mission profiles. Robust thermal management and radiation shielding are also essential to protect both the crew and sensitive onboard instruments from harmful cosmic rays and particle blasts. Furthermore, experimental models and computational simulations continue to refine our understanding of propulsion dynamics under extreme conditions. Research institutions and aerospace companies globally are collaborating to design test beds and scaled experiments, gradually bridging theoretical models with practical engineering. Each incremental improvement, whether in microscale ion thrusters or macroscopic nuclear propulsion systems, contributes valuable data towards an eventual synthesis of technologies capable of powering intergalactic voyages. It is clear that the challenges are formidable, yet the progress in propulsion technology remains one of the most exciting frontiers in modern aerospace engineering. Innovative propulsion research steadily transforms theoretical limits into experimental milestones, propelling our journey from distant dreams to foreseeable realities with each breakthrough achieved. Progress is unstoppable. Designing spacecraft for intergalactic travel is an engineering endeavor of unprecedented scale that necessitates comprehensive innovations across multiple domains. The basic infrastructure must incorporate a robust modular framework to allow for redundancy and in-field repairs throughout a mission that may span centuries. One of the most significant engineering challenges is the integration of life support systems that not only maintain a habitable environment, but also provide reliable means to recycle air, water, and food. These systems must sustain biological functions while simultaneously operating under conditions of microgravity, extreme temperature fluctuations, and high radiation. Resource management takes on a critical role in long-duration missions. Engineers need to design closed-loop systems where resource generation and recycling are maximized. For example, advanced bioreactors could be employed to convert carbon dioxide into oxygen, and hydroponic systems might be optimized to produce food, all while minimizing energy consumption. Energy production infrastructure is equally complex, with an emphasis on developing nuclear or fusion reactors capable of providing consistent power output over timescales that dwarf contemporary missions. The incorporation of superconducting materials and energy storage devices further enhances system efficiency and reliability. Thermal regulation and structural integrity are also paramount. Spacecraft must be engineered to withstand not only the rigors of deep space, but also continuous exposure to cosmic radiation and micro-impacts from interstellar particles. Redundant communication systems, advanced diagnostic sensors, and autonomous repair mechanisms are essential to anticipate and mitigate failures. Moreover, the design must factor in the potential need for artificial gravity, whether through rotational habitats or other innovative means, to counteract the long-term deleterious effects of weightlessness on human physiology. The integration of these elements into a cohesive engineering design demands a multidisciplinary approach, combining aerospace engineering, materials science, and systems biology. The lessons learned from extended missions aboard the International Space Station and long-duration deep space probes serve as valuable blueprints for overcoming these daunting challenges. In such an ambitious project, every component from microscale circuitry to macroscale structural supports must be optimized to ensure sustainable, real-time operation throughout an intergalactic voyage. Through rigorous testing and continuous refinement, engineers are steadily advancing the infrastructure needed for enduring intergalactic travel, ensuring mission safety and operational longevity. Without compromise, at the heart of intergalactic travel theory lies an advanced understanding of the intricate relationship between space-time and energy. Einstein's theory of relativity has fundamentally reshaped our perspective on motion, mass, and time, particularly when velocities approach the speed of light. In the context of deep space missions, time dilation effects cannot be overlooked. As speeds increase, time aboard a rapidly moving spacecraft diverges significantly from that experienced by observers on Earth. This phenomenon introduces both challenges and opportunities for synchronizing mission timelines with galactic dynamics. The allure of wormholes as potential shortcuts through space-time has captivated theoretical physicists for decades. These hypothetical tunnel-like structures, predicted by solutions to the Einstein field equations, suggest that regions of spacetime could be directly connected, bypassing the vast distances between galaxies. However, practical application remains elusive due to the requirement for exotic matter, substances with negative energy density, to stabilize and keep wormholes traversable. Moreover, the stability of such formations under quantum fluctuations remains one of the most intriguing unsolved problems in modern physics. Beyond wormholes, quantum entanglement and other non-classical phenomena provide thought-provoking avenues for exploration. They challenge conventional notions of causality and signal propagation in space. Scientists continue to investigate if quantum effects could eventually be harnessed to establish instantaneous communication channels, or even propel spacecraft by exploiting quantum vacuum fluctuations. These concepts, while sounding speculative, are supported by rigorous mathematical modeling and experimental hints that defy classical intuitions. Emerging research in high-energy particle physics and quantum gravity offers additional insights into the fabric of the universe. As we refine our theoretical frameworks, the boundary between science fiction and feasible physics gradually becomes less defined, offering a promising glimpse into the future of intergalactic travel. These robust theoretical models are continually tested through both astronomical observations and laboratory experiments. Their outcomes inspire refined equations and predictions that underpin our quest for practical implementation of intergalactic travel technologies. Intergalactic travel is not solely a technological challenge. It also raises profound societal and ethical questions. At an expert level, the discussion must consider not only the allocation of vast financial resources and research efforts, but also the possible long-term impacts on human civilization. The development of intergalactic travel technology forces us to confront issues of global inequality, where access to cutting-edge space infrastructure could be limited to a select few nations or private entities. Additionally, questions arise regarding the responsible stewardship of resources, both on Earth and in space, as ventures into the cosmos demand enormous energy inputs and potentially disruptive mining of extraterrestrial materials. Ethically, the prospect of sending humanity on one-way, multi-generational voyages presents complex dilemmas regarding consent, societal organization, and the preservation of cultural heritage. The psychological and physiological impacts on those undertaking extended journeys across light years must be rigorously evaluated, ensuring that potential risks are minimized and balanced with the expected benefits of new knowledge and survival prospects. Furthermore, initiatives in intergalactic exploration could redefine our understanding of life and our place in the universe, prompting a re-examination of philosophical and existential beliefs held for centuries. As discussions progress, policymakers, scientists, and ethicists must collaborate to establish guidelines that promote safe, equitable, and sustainable exploration. Comprehensive international agreements would be necessary to govern the deployment of intergalactic missions, ensuring that technological advancements benefit humanity as a whole, and that environmental impacts, both terrestrial and cosmic, are responsibly managed. Global ethics must guide progress. In summary, the journey towards intergalactic travel involves a convergence of advanced engineering, deep theoretical physics, and bold innovation. The challenges are as formidable as the distances are vast, yet our growing understanding of propulsion, energy generation, and life support systems continues to push the boundaries of what is conceivable. The improvements in computational models and a relentless commitment to overcoming technological hurdles have moved the prospect of reaching another galaxy from speculative theory to a roadmap for future exploration. The integration of multidisciplinary research, from quantum mechanics to advanced material science, paves the way for unprecedented breakthroughs that may eventually enable sustainable intergalactic voyages. This vision is not limited to technological triumphs. It encompasses a broader reimagining of human society, ethics, and our place in the cosmos. As we refine our methods and expand our horizons, international cooperation and comprehensive policies will be indispensable in ensuring that these radical advances benefit all of humanity. Our collective quest for knowledge and survival drives us to explore the unknown, inspiring future generations and challenging the boundaries of science. The future of intergalactic travel may be distant, But every incremental discovery lights the path toward a reality in which another galaxy is within our reach.